Welcome to the third video lecture. This lecture will be talking about text data specifically, and it will be a two-parter, so this will be part one. Now let's first go into detail regarding what we're going to discuss. So we'll be talking about representing text as vectors, about binary representation of these vectors, and how to handle these with decision tree classifiers. We'll then get into using vector spaces for classification, doing some weightings with these text vectors, and then finally we'll discuss classification using k-nearest neighbors for documents. So you might be wondering, why are there two separate lectures on text data? Now, text data is a lot different than what we have worked with up until now, which are mostly numbers, mostly numerical data. Even though they might still be very complex to interpret for classifiers, they don't have a lot of ambiguous information. Numbers are numbers, there's a number system, they range and scale within a certain distribution, and therefore they have some limited information they can provide. Now, language as a communication tool for humans is inherently complex, because we need to communicate a lot of complex information. Now, this brings up four main issues. First one being that representing language is very complex. Obviously we have words, they have certain separators, but the words alone aren't enough to capture the richness of information that is usually contained within a certain message. Now, that also makes mathematically interpreting language very complex. We can't just rely on words being in a certain text, yes or no. They also have a certain semantics, certain information they conceive within a document. And from there we can say that, well, inferring this knowledge from language as being this symbolic system is also very complex. The words by themselves don't capture the full world knowledge that we have, and therefore this is not something that is easily done. And then finally, when having a representation that we might use to infer, understanding the message correctly is also very complex. We as humans even struggle doing this. Information might be ambiguous, hard to interpret, there might be irony in there, these kind of things. And you can imagine this is super difficult for just simple algorithms. Now, just to give you some small example, I've prepared this imaginary message. You can say that maybe it's like a Twitter message, and it says, "Just Netflix pixels, best time ever, lol," and then 1 out of 5. So let's try to sort of deconstruct this message as we would as humans. Now, we have to know that Netflix is a platform that provides videos. We also have to know that Pixels is a movie that you can see on Netflix. Now, knowing that this is a movie, we can see that this 1 out of 5 is probably a rating that this user is giving to this movie. But as you can see, we already need a lot of world knowledge to actually come to this conclusion. And then the last part, best time ever, we would probably interpret as being very positive if we didn't consider the rest of the message. But given the fact that this movie got 1 out of 5 stars from this person that posted this message, and there's lol right here, this is probably meant as sarcastic. So even in this very small message, there's already a lot of information that is not just captured by the words that are in this message alone. So how do we represent language? Usually for representing it in a certain data set, you can see that there's generally when there's, for example, this CSV with movie information, it usually shows up as a string, as we call it. And a string is a piece of text that is captured between these quotes here. Now, it can vary from a single instance, like the movie title here, It can be a bit more complex, like a name, which obviously has a first and last name. And then once we get to the plot, we get actual running text. Now, just viewing this as a string for a computer is just a bunch of bytes, and each of these values will be unique when a computer looks at it. So there's no information yet that the computer has on this string representation right here. So how do we actually get from these strings to some representation of information that algorithms or computers in general can actually work with? Or how do we represent them as vectors? Now for this, the challenge is to go from some string input that we have that is a small sentence to a actual vector that should contain numbers, right? That's how we know a vector is as a sort of position within this vector space. And once we have this representation, we can actually do some algorithms. So in sum, we would want to convert this string to numbers. Now, one way of doing this is looking at each word as features within a bag of words representation, as this is called. Now, the bag of words representation assumes that each word in a sentence is a feature and that the order of the words in the sentence doesn't matter. So if we would convert this to a sort of binary format where we just want to say if a certain word is on or off in a sentence, and this is the only instance that we have, then obviously all the features are going to be these words. Right, that we sort of deduce from the sentence that we have here. And obviously double words won't show up. Now once we get this, you can see that this is just alphabetically ordered, and every word in this sentence is on. Basically, all the words are thrown into a bag, they're scrambled, sorted, and counted. This is what a bag of words representation implies. Now for the previous sentence we only had one example, now we have two, so not everything is on for each document. So this would be document 0 and this will be document 1. Also notice that now we're referring to the vectors that we had before, x0 and x1, we actually refer to them as documents. This is why we use D rather than X, which is a bit more specific. So looking at these, you can see that for the sentence, my cat sat on my cat, there is cat in this sentence, there is no mat, there is my multiple times, cat is also in there multiple times, but given this is binary, we're just interested in if it's on or off. And then you can see the rest of the sentence here. So this would be a binary vector representation of these two sentences, and then this whole thing would be our feature matrix, where the features are now words. Now notice that to get to this representation, for a string format we need some way to indicate where the boundaries between words are. Luckily we have this visual separator, which is a white space, and this is generally used to split a string, as this is called. So if you would have a piece of code, this would look like d0.split, and then we define that it's a white space like this, and this would split up this string into a list of words. Just to quickly go through how to do this in code. Alright. So the two representations that we get with this is one feature matrix, as I indicated before, but we also have a vocabulary. Now the vocabulary is implicitly encoded by some index. So if we would want to have let's say x, I, j, where I are the rows and j is an index for the columns, then if we would call x0 and then j is 1, then that would point to this one right here, and that maps to cat. So the index v1 is cat. And this representation we don't necessarily need when training any algorithms on this, because as you can see, these are not numbers, we can't use them. But if for any reason we need to map these features back to the actual words, we keep the vocabulary handy. And keep in mind that the vocabulary is just a set, so there's no double words in the vocabulary. Each word just maps to one index in our feature space. So now we have this binary representation of language, basically of text data. We can look at a bit more interesting example where we have 3 Wikipedia articles. Here is the vocabulary, so we have data, language, learning, etc. And then here's our target, which is a label for the topic that the article is on. So you can see here we have computer vision, natural language processing, and text mining. So X will be this this matrix, which you can sort of fill in yourself. Then Y will be CV, etc. And this will be V. Now if you look at this visually, you can sort of distinguish these 3 vectors just by the fact that certain words are on and off. So the fact that mining is in here and is not in computer vision or natural language processing already gives some indication that this concept is not really that important for these 2 other fields. Now you can also see that natural language processing and text mining both deal with text, and then for some reason language for text mining is off, probably because language is not necessarily the focus here. Now if we want to have this sort of visual intuition that we had from this previous slide into a bit more of a formal construct, we represent these 3 documents as actual vectors, and we can give a sort of similarity between these documents using the Jacquard coefficient. Now the notation of the Jacquard coefficient is quite straightforward. We're interested in the words in both document A and B, so this might be, for example, D0 and D1, and then we divide that by the words that are either in A or B, so this part will generally be smaller than this part. So we're interested in the overlap and then divided by the total amount of words. Now just to take one example, we can take document 0 and document 1. We can see that from this little comparison here that there's only overlap between these over here and these over here. So there's 2 words that are shared between these 2 documents. And then if we check all the positions where there's a 1, so it's 1, 2, 3, 4, 5, this is the full vocabulary between both of these sets. So you get 2 divided by 5 equals 0.4. So the Jacquard coefficient between these documents, which we can sort of say relates to some kind of document similarity, is 0.4. So here we can see, if you remember, this was NLP and text mining. You can see that they have a bit of a bigger overlap between each other than computer vision has with any of them, which intuitively makes sense. Alright, so far we've been talking about a very straightforward way of representing data as binary vectors. One of the algorithms that can handle binary input very well are decision trees. They are not restricted to binary data per se, but it's just that the trees that are constructed are very clear to read, and going through the algorithm is actually easiest with binary data. So for this lecture specifically, we'll focus on the ID3 algorithm implementation for decision trees. Okay, so let's consider these documents that we had before. If you would want to classify them with Y being the label, we already discussed certain rules that we might be able to use for this. So for example, if language is in there, if text is in there, if vision is in there, these seem to be sort of the characterizing terms for the different documents. Now if you would only focus on the unique terms, then language obviously maps to NLP, mining maps to text mining, and vision maps to computer vision. Now, if you would want to cast this ID into a few rules, this would look somewhat like this. So if the term vision is in the document, then we label it computer vision. If it's not in there, so else, we check for another word. So if language is in the document, then it's NLP, and if these two conditions aren't met, it must be text mining. Now, for this small set that we have here, this will cover all of the examples, but you can imagine that in the case that a text mining document does have the word language in it, we're going to misclassify it, and obviously these are very overfitted rules. And this brings us back again to this idea that we can create custom rules if we want to, but given that we probably have many documents, we would want to find some way to automate this. Now, this sort of intuition for rule construction is captured within decision trees. So let's look at this this task right here, where we have a standard sort of text classification task where we're interested in spam detection. So let's say you have your email has some words in there, and we want to know if we have to chuck it in the junk mail box, or it can stay in your inbox. So the ones that we label as spam are called spam, like this, and then the ones that we think are correct emails and shouldn't be chucked in the junk mail are called ham. We have our labels here, so it's either spam or ham. There's some words that are either on or off. So in this document, free is on, money is on, account is off, transfer is off, and it's labeled as spam. And we're going to use information gain to make an informed decision on which of the features is actually most informative to classify a certain label. This is what decision trees do. So say we have our question is an email spam, then we would want to have a feature here that with a very high certainty splits the instances of spam and ham in the tree. So let's assume that this is our feature free. If we look at the instances here, we can sort of visually see that most of the messages that have free in them are actually spam. So this is probably a safe assumption. So our first feature that we consider is free, and we split this into if it's not in there or if it is in there, and we base our decision on this. So if we look at this, at some point we'll run out of features to use. So let's say the second one here, just on top of my head, is account, and then here it's money, for example, and let's say these are the last features that we're considering. Then at the end, so at the final nodes, we need to make some decision. So we'll say this is spam, this is ham, and this is ham if it is in there, and if it's not in there, it's spam. Same goes for here. If money is in here, it's spam, and then if it's not in there, it's ham. So we can chuck any email in here and ask the question, is this spam? Now we just descend down the tree to check if the words are in here. So if free is not in there and money is not in there, it's probably spam. This is just some residual rule that we have. But if money is not in there and money is in there, if free is not in there but money is in there, it's probably good. But if free is in there and account is in there, we can consider it as a safe email. But if free is in here and account is not in here, then it's probably spam. Now these are just some very quickly drawn rules. This is definitely not how the actual tree will look like. To make the actual tree, we need to calculate the entropy and information gain for each feature that we want to consider splitting our feature space on. Now let's consider looking at this from a sort of feature space ID where we have our words on axes, so free, money, and account. Now the ones that have free and money in there as we said, will probably be spam. And then the ones that are here, 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 etc. are probably ham. So by making some rules saying that if money is 1 and free is 1, there is this decision that the tree makes, sort of invisible decision line that says anything at this side is going to be classified as spam. Now the rules are actually usually orthogonal like this, but just to illustrate I drew a diagonal line. If you look up decision trees, there's very nice visualizations of the decision boundaries that this algorithm makes. So let's go into the math. Now notice that the algorithm uses information gain and entropy, which are both concepts that are related to information theory. This is not an information theory class, so we will not be discussing these concepts in theoretical detail. If you're interested in their foundations and work, you're welcome to look this up, but we'll just assume here that these are the formulas for entropy and information gain and just roll with them. So let's look at the first formula. This is to calculate the entropy of a single instance, so this is for the class only, and generally we will refer to this as y rather than c, but the formula stays the same. So to calculate the entropy over a class distribution, so this will be over this whole column right here, we take the sum over the classes, so spam and ham. If we had 3 classes, these would be 3 iterations, and for each iteration we calculate the proportion of the class given the total amount of classes. So if we calculate the entropy for ham individually, this will look like this. So there's 4 instances of ham in our data set, if you can see here. So 4 times ham. And then our total data set is 9 instances, so this will be 4 over 9. And then for the second part, we take the logarithm with base 2 of 4 over 9. We multiply these, and then this is the entropy for ham. We can do the same for spam. Now we have 5 spam instances, as you can see, so it's exactly the same. 5 over 9 logarithm, and then we get the entropy for spam. Now to get the entropy for the full distribution of labels, we add ham to spam. This is incorrect. And this will just, if you calculate this, it will be 0.25. This will be 0.47. And then if you calculate this part, it will be 0.991 as the entropy over the class distribution. So you might be wondering, why did we do this? This is what we'll get to in the next slide, right here. Now to calculate information gain, we need to have a entropy before, as this is called. So we have entropy before, and we want to compare this to the entropy after making some split in our data. So the entropy before at the very root of the tree is just the entropy of y that we calculated before, and then the entropy after is whatever we decide to split our data on, so make a decision on if it's either yes or no. As I said in the example before, the first feature we'll be looking at is free. So free can either be off or on, and then this is divided between when it's spam or ham, and just for convenience I made this total column right here, which helps us with filling out the formula on the next slide. Now to calculate the entropy for 2 attributes, so both the feature as well as the distribution over labels, we have this summation, and we want to weight with the proportion of the class that goes down each tree. The information gain, just to quickly specify, is given by the entropy of y minus the entropy of free y. So this part we already have, and now we're interested in calculating this part. So free has two values, so we only need to do two calculations. Imagine if this had more values, we needed to repeat this as many times as there are values. And as it is, this is already a mess. So just to go through this formula to calculate the entropy of free being not in there, given the label distribution, we have this proportion here where free is 0 and spam times the same, but then the logarithm. And we do the same for when free is 0 and when the label is ham. Exactly the same here, but then for free is 1. And then when we put this all together, we want to have this weighting in here. So we do the proportion of free 0 times the entropy of free 0 y plus p free is 1 and then times e free 1 y. Now you can just very carefully go through this notation. I'm just going to go and skip ahead to the solution, but we'll be filling in all of these looking at this table right here. So free 0 spam, we'll look up free 0 spam, so that will be 2 over the total, and the same for free 0 ham, that will be this one over the total, etc. So you can skip sort of between the beginning and this slide to see where all the values are coming from, but we just fill it out as we go. Just to note though that the values in this table right here don't correspond to this ones because I made some last minute changes. This is the actual one, so the other one is incorrect. Okay, so here we can see that for free 0, and then this is the spam part, we have 1 over 4, and then for ham we have 3 over 4. Same here for free is 1, we have 4 over 5, and then 1 over 5, and then the weighting is the total. So for the proportion of free is 0, we have 4 over 9 times this, and then for free is 1, we have 5 over 9 times this, and this will give us the entropy for free given y. And then for the information gain, we just fill out what we had before, so that is this 0.991, and we subtract that from the solution of this one, and then we get 0.229. And this will be the information gain for this particular feature. Now to get the information gain for the other ones, you repeat exactly the same thing. So we have this this split again, but then for the other features, we'll get basically an information gain per feature. So free, we get an information gain for money. Then in the end, we pick the one with the highest information gain to be our first split in the tree. Then we repeat this thing again with all the features to see which then has the highest information gain with the leftover features. Now this looks somewhat like this. So say that we wanted to go for spam. We decided to do it on the feature free. There's going to be some amount of instances that are classified under this tree and some under this tree. Given the fact that we assume that when free is 0, it's going to be ham, there's still one misclassification right here that we need to split up. So this will have 1 spam and 3 ham. So this part will have 4 spam and 1 ham. And then for this we will make, for these instances specifically, we'll again do exactly the same operation, and then for these as well, to devise a split for these leftover features. This repeats and repeats until everything is classified or we hit some stopping criteria. So just to recap the what I said, I have it on the slides here so you can read it, but it basically says what I said before. And I think the easiest way to get a better visualization of it is to check out one of the pages that I supplied for the supplementary material, which is a visual introduction to machine learning. If you scroll down, at some point it will start explaining how decision trees work, and you can very nicely see the distributions that it uses to make certain decisions. And then especially for this one, you can actually see the rules and how many instances go in which bin, also for a test set. And it has a very, very nice JavaScript visualization of which rule classifies which instances. So I advise you to check this out and also read the text. And if that is not enough, then there's a few threads and web pages explaining it in the small quote block over here. So up until now we've only looked at words in a sort of binary format, but it's not very convenient in a vector space because we actually want to use the fact that we have continuous features or feature values to make more advanced classifiers that will not only handle the fact that a word is on or off, but also when it occurs more often, it might be more informative. Now, as I said before, binary is a very compact representation because it's only zeros and ones. So in terms of memory, it's very efficient to store your feature matrix like this. You can even use sparse matrices, and they require certain implementations, but they have a very small memory footprint, which is very good if you're working with very large data sets. However, they also say very little about the weight of each word, so they don't have more information than the fact that a word is only in the text doesn't say when it's 100 times in the text. So you lose this type of information. Now, on another upside, decision trees and several other classifiers work very well with binary data, and they actually become very interpretable because it's only yes or no, and you get this real rule output. However, as I said, we can't really use the vector spaces to our advantage using binary representations, and this is something we ideally want to do. So rather than binary representations, we use term frequencies. Now, before we get into term frequencies, let's discuss a bit of notation. I think the notation here speaks for itself. You can sort of pause the video, but just so you know that when referring to either dt, di, ti, vector d, term frequencies and all these kind of things, you know what we're talking about. Conceptually, term frequencies are very easy, just the amount of times that a word occurs in a certain document. Then the terms before were our vocabulary, and if we sum over all the term frequencies, we get the word length of a certain document. This is all pretty straightforward, just to sort of show you the math and the notation. So just to very quickly give an example, given the two documents that we had before, the cat sat on the mat and my cat sat on my cat, rather than having this 1-0 representation, when a word occurs multiple times, we actually have the amount of times that it occurs within the matrix. So cat occurs 2 times in D1, so therefore there's 2 2's here, and then we have the vector of document 1 looks like 202, 110, exactly the same as this one. So pretty straightforward. So let's put this method to the test. I got 6 Wikipedia documents here. So this is just a flat text of the Wikipedia articles on natural language processing, information retrieval, artificial intelligence, machine learning, text mining, and computer vision. And when we get all the term frequencies for all the words in these documents, we get a very nice term frequency representation that we can use to sort of inform ourselves how important certain words are in terms of term frequency when we look at the index of a certain word. So remember that our vocabulary or our term matrix has an index that we can use to look, sort of peek in our feature matrix to see the representation of a certain word in terms of the frequencies for each document. So say we look up the term learning, and then in this matrix over here we can see how many times the word learning occurs in any of these documents. So these have a one-on-one mapping, so D0 is this one. So learning occurs 27 times in natural language processing, only 2 times in information retrieval, 46 times in artificial intelligence, etc. Now it's pretty logical that the term learning will occur most in machine learning and in artificial intelligence, and not so much in, for example, information retrieval. So already we can see a sort of divide between these documents. However, if you consider the information that term frequencies give us, is the term learning very relevant, very much relevant in artificial intelligence? It is, probably. However, is it also the factor by which it is higher than, for example, the 10 in computer vision? Does this reflect the amount of information? So is it 10 times as informative? Now it turns out this is not very realistic, but information theory has a solution for us, which is to take the logarithm of these frequencies so they sort of scale naturally, and therefore have a better relation with actual information. Now to do this, we just apply the natural log to each term frequency, and there's a very small smoothing operation going on to avoid taking the log of a term frequency of 0, which will result in minus infinity. Now the smoothing is optional. You can decide to only do it when the term frequency is 0. You can decide to always do it. These are sort of choices that you make while sort of processing your data. Now once we apply this logarithm to all these frequencies over here, this is the matrix that we're left with. So you can see that this 134 here now has a way less impact compared to, for example, the 10 in computer vision. So we get a sort of a nicer scale where it's harder to go up very much with big numbers. Sadly, we didn't solve all our problems yet just by taking the log of a bunch of term frequencies. One of the things that might be most problematic is the fact that if a document is longer than other documents, then artificially this term frequency will increase. And it doesn't scale with this sense of information that we have, or that we wanted to achieve by taking the log. Alternatively, the rare terms now have a very low weight, while maybe we think that these are actually more informative than words that occur a lot. So you might think stop words, for example, like the and a, etc., will occur a lot, and they are not really informative. So we want to have some sort of measure that captures the rarity of a certain term. What we don't want to capture, however, is rare terms that only occur in one document, because they will probably just be some outlier. The thing that we're very interested in is terms that only occur in few documents, because these rare terms will probably be very informative for these this limited set of documents. They will probably have some indication that these are very similar because these rare terms only occur in these few documents. So I've said the word document a lot. You can already see that this sort of alludes to using the document frequency for an additional sort of weight or indication of information. So we can look at document frequency or inverse document frequency to be extra specific. Basically, again, the intuition is very easy. We just check a certain term and how many documents it occurs in. So the frequency of the term doesn't matter. We're only interested in the count of the documents in which the term occurs. So let's again consider our Wikipedia articles. We have the term naive here, and we can see that it occurs once in the first document, twice in the third document, and 3 times in the fourth document. But regardless of the term frequency, we say that the document frequency for this term is 3 because it occurs in 3 documents. Now, to create this sort of measure of informativeness, we actually want to punish a certain word frequency by weighting it with its inverse document frequency. So hopefully this will capture the fact that the more it occurs, the less we actually want to give weight to it, because it will probably be a very common term. And this way we sort of zone out the stop words, the very common words that are very uninformative for our entire collection of documents in total. So the formula is just take the logarithm with some base. Commonly for IDF it's 10, but it doesn't really matter. You can also take 2 or the natural log, whatever you decide on. And then you take the log of 6 over 3, so that the total n right here, that is the total amount of documents in our collection, and then we divide it by the document frequency. So for naive, we have 6 documents, so it's 6 over 3, and taking the log, this will give us 0.30 as the inverse document frequency for this specific term. Now you might have already sort of seen where we're going with this. If we combine this nice metric that we have for term frequency that is weighted with the logarithm with the inverse document frequency, we get a nice representation that is called TF-IDF. Now TF-IDF is very, very popular as a representation for words in certain documents. It's actually a very stupid representation because it only uses these very old concepts like term frequency and document frequency that are mostly information theory driven to weight frequencies. It turns out that if you use this for example, information retrieval system, where we're interested in seeing if a certain query is related to which documents, which you might know better as a search system like Google, this is a very, very effective metric. Now, just to give you some very quick indication of how it would work in information retrieval. Again, this is not an information retrieval class, but it's always nice to show some additional practical example. The only thing that we would do to retrieve certain documents using TF-IDF is that we apply TF-IDF weighting to the entire collection of documents that we have. These might be, for example, Wikipedia articles, they might be scraped websites, and then our query vector is exactly the same as our document vectors, but again, we probably have way less words in our query, but at least we have some weight to them, given the fact that we know the document frequencies from the training set or our entire collection, so we can weight these, and then we get an extra vector for a query. So let's assume this is 0.4, 0.1, 0.9, and then maybe even 1.5 here. Now, depending on the weightings that we have here, we calculate the distance between our query and these 3 documents that we have, and then in the end we would want to say our query is most similar to document 0 at first. So we retrieve in a list that is ranked, we will give 0 as first, maybe 2 is actually the second, and then 1, and this is how, by similarity, we give a certain return for the query. So assuming that Google uses TF-IDF, they don't, but let's assume that they do, then this would be the way that they sort websites according to your query. Anyway, just to round this up, this is the formula, full formula for TF-IDF. Here's for a bunch of these frequencies, there's a weighting. And the most important thing here is you can see that because text is in every document, it is assumed to be super unimportant. So all these actually get a weighting of 0.0 because this part will be 0. And you can see, because intelligence is actually a rare term, it gets a higher weighting than learning, for example, which is a bit more frequent in 2 documents. So far we've fixed sort of how we represent information in a nicer way than just using frequencies or binary representations. But despite the fact that we use TF-IDF, we still don't account for the length of the document. So longer documents will still be weighted more, even under TF-IDF weighting, and we have to do something about this. And why I will illustrate in a practical application using k-nearest neighbors algorithm that uses certain distances and the labels of certain instances to make classifications. So at training time, it remembers the position of all these instances in the vector space and their labels. So it knows that the blue dots are class 1 and the red dots are class 2. And then at test time, if we give it a new instance, it will try to classify it based on the most nearest neighbors. So say that we have case 3, and these 3 will be the closest instances, and therefore it will probably be classified as blue, and therefore class 1. That's a very, very shallow explanation of how K and N works, and that's why we are getting into more detail on the algorithm now. So how does K and N have this sense of these neighbors are actually my neighbors of this training instance? And one of the metrics that we might use is Euclidean distance, which takes 2 vectors, then takes the sum over the squared of these vectors minus each other, and then square root, and that will give us a sense of distance as we would measure with a ruler. So say this is one instance and this is one instance, then the Euclidean distance is just this distance over here. And how do we know this? Well, we know the coordinates of this one, we know the coordinates of this point, so we know the distance from here to here, and we know the distance from here to here, and then magically it becomes a triangle, and we can use the Pythagorean theorem to calculate the Euclidean distance. However, there's one problem with Euclidean distance, which is when documents are longer, their vectors have more weight, and therefore they are way further away than documents that aren't so long and are probably on the same topic, which is problematic for text classification. For most other sort of applications, this isn't really a problem, and therefore Euclidean distance is fine. But given the fact that the weight of our vectors in this example is important, this is something we care about when dealing with text. Now in comes L2 normalization, which takes the unit vector length of each vector. Now this is the formula, which is also pretty straightforward, and what it will do to our instance space is that these instances that were previously sort of scattered around will now be normalized, and therefore they will all sort of conform around this one specific axis like this. So their distances from the origin should all be exactly the same. However, we can still calculate the distances in between these. Now it's important that the L2 norm, this formula is just to actually get the norm, and the norm you would want to apply to your vector. So say that we have some vector 1 with 2, 3, 1, and then say that our norm will be 0.2. This is our L2 norm. Then we apply the L2 norm to this vector by just dividing all these values by 0.2. Now once all our vectors are normalized, we can take the dot product, which is indicated by this, between two vectors to get the cosine similarity, which is the distance along this nice circle that we have here, where now all our instances reside. So basically getting this distance over here, and this is just the element-wise multiplication. So given that we have two vectors, so let's say vector 0 and vector 1, to get the dot product we multiply 1 by 2 plus 2 times 3, and this will give us the cosine similarity between these two. Now for the previous data mining iteration, I wrote a small blog post to compare cosine similarity and Euclidean distance. I will add it to the reading materials. It does sort of a practical comparison between these two metrics. It will shed a bit of light on these. So now that we know how to weight our vectors, have a certain sense of a good representation of information, a good representation within our feature space, and then also a metric to calculate the distances between our vectors, we're almost done with implementing KNN. Because as you might recall, KNN is not more than just storing the entire matrix X train within memory, and then it just calculates this distance metric between some test instance and all of the training instances. So just to quickly draw this up, here's our feature space. These are the ones that we got in X train. So all these instances are X train, and then this one little dot here is our X test instance, and it will just calculate the cosine similarity or the Euclidean distance, whatever we decided on, between all of these, so all of them, literally all of them. And then in the end we get a nice list with all the similarities between our test instance and the vectors that we have in this space. And then we just choose the ones which have the highest similarity up to k. So say that we have k is 5, we will choose the 5 that have the highest similarity. Then we can look up in Y train what the labels were of these vectors. So for k is 5, we get a list of 5 labels. So say this is class 1, class 1, class 1, and then we have 2 with class 2. Then we just do a majority vote, and we say our classification is class 1 for this guy right here. Now one of the first questions you usually ask is, what happens if we have a even k and we have a tie? Well, we can do some augmentations to our KNN algorithm. They are listed here. So other than using either Euclidean distance, maybe Manhattan distance, or cosine similarity, we can also weight our labels by, for example, the frequency of the labels. So we look at the distribution. Just to quickly draw this, say that we know that class 1 actually has a frequency of 50, and then class 2 has way more, so that might be 100, and then class 3, for example, has 20. Now we can say class 2 is most common, so it might be safest if we actually guess class 2 because this is the majority label within our data set. We might also weight them by the inverse frequency, so actually go for the rarer ones if we have a tie. But we can also weight this decision by distance, so if we, for example, have very far neighbors, so say we have case 4, then this guy will probably be a lot more like our test instance because it's closer, so we can do something with these distances to weight our labels. And then conveniently doing this, we always avoid ties. But also it improves the quality of our decisions over just doing a naive, let's just look at these k amount of neighbors. So that concludes the first part of working with text data. Next lecture we'll look at some practical applications as well as some issues with language, and hopefully this was an informative lecture. If you have any questions, you can post them on the forum.